Welcome to a new episode of Hidden Gems. Today, I'm here with my colleague Pranay Walson, who leads the engineering efforts in the Covalent Network. We have an exciting piece of technology that we're unveiling today. Pranay, how are you today?
I'm doing great. Yeah, it's a pleasure to be here and talking about the release of the things that we've been working on for the past 1 year.
So, what we're releasing to the world is the refiner. And what is a one-sentence description of what the refiner is?
Well, the refiner brings unparalleled insight into blockchain data through concurrent re-execution technology. I would say that's like, in a very technical sense, a one-liner for the refiner. From a business-oriented sense, I would say it allows you to drill down into blockchain data without the conventional problems of sequential processing that blockchains have, or JSON-RPC roadblocks.
Okay, There's a lot to unpack here, so let's go through this step by step. Let's talk about how we got here. So the Covalent Network was just a glimmer of an idea a couple of years ago as we decided to re-engineer Covalent, the product, and the underbelly of the Covalent Network to be a decentralized network. And then you've been working on this full-time for the past couple of years. It's been your baby from day one. And you even moved to Canada to take on this initiative. So very appreciative of that commitment. Let's talk about how we got here. What is the Covalent Network? What was phase one? Why phase two? And so on.
The inception of the Covalent Network was primarily to decentralize data access. And what we found was there are systems that exist that currently ingest the blockchain node data and keep it in a centralized store. But we wanted to come up with a way where we could horizontally scale access, make it more transparent, and democratize access to this data. So the Covalent Network is basically the baby of this kind of ideology. And the phase one was basically putting out into the world a specification for how we would extract this data from a blockchain node, irrespective of the underlying blockchain. At Covalent, we're pretty good at understanding how data needs to be structured so it can be accessed by businesses through an API, so like a unified schema. And so the core product of the phase one was the specification and the producer of this data object that produces the data in the specification. And the coming phases, of course, tie in to this exported data, analyzing it, being able to transform it, being able to re-index it, and finally serve it through requests in a decentralized manner. And of course, underlying all of this is the CQT token that allows the interactions between the different components of the Covalent Network.
Incredible. One question I get a lot from the community is, how is Covalent different from the graph? So ideologically, philosophically, it's very different from the graph. So maybe let's touch upon this ETL versus ELT paradigm that is butting heads with the graph's approach. That's another alternate approach. There are pros and cons to each. The two paradigms in data processing and data pipelining is ETL and ELT. And this acronym stands for extract, transform, load, and extract, load, transform. So it's just the different stages of the data pipeline, just inverted. So in the graphs approach, which is a standard ETL paradigm, what you do is you extract data from the blockchain, you write a subgraph, which is the transformation of this extracted data, and then you load it into a data store, and then you query the data store using any query language. In the case of the graph, it uses GraphQL, but it could be REST APIs, it could be a binary protocol. It's just a query interface. So that's the ETL pipeline. In the case of Covalent, it actually does things very differently. It's the ELT paradigm where we extract data from the blockchain, all of the data, and load it into a data store from the get-go. So you now have this database with all of the data from the Genesis block. And then at query time, that's where you do the transformations. So the newer technologies that are facilitators is the cloud native scaling, block execution, column compression. A lot of these things enable a transformation at runtime as opposed to ahead of time transformations. Now, this manifests itself in its use cases in multiple ways. The key difference is that in the ETL paradigm, if there are any downstream changes or any upstream changes, you have to go back and build that transformation engine and re-ingest the data. So what does this downstream, upstream changes mean? Upstream could mean a change in the blockchain. So in Covalent, for example, we've indexed over 100 chains. And so something like a proof of work chain like Ethereum is, from a data perspective, it's exactly the same as something like Boba, which is an optimistic rollup. But in Boba, you pay using 2 gas tokens as opposed to just ETH in the case of Ethereum. So that's a change in the upstream that needs to manifest itself in this transformation engine. So as you add more and more and more chains, the transformation engine has to keep modifying and re-indexing the data before it is able to capture all of this disparate data sources. On the other side, changes in business requirements. So for example, you want to aggregate monthly as opposed to weekly. In the case of the ETL, the subgraph approach, you build these roll-ups ahead of time. Basically, you have to have entire, like, full requirements gathering and build all of that in the transformation. And if there's any change in those business requirements, you have to go back, rewrite the transformation, and re-index this. This is a big deal. So something like the Uniswap subgraph, for example, it takes about 7 days to re-index the data. So that's really the issue here. With the Covalent approach, the transformation is at runtime, which means if you want to aggregate weekly or monthly or daily, whatever you want, or some new metric, it doesn't matter because the data store has all of that data. So that's the fundamental difference between the two. And this philosophy has taken us pretty far. There's a whole bunch of use cases that only Covalent can address. So a good example there would be taxation, where you might have a transaction anywhere on the blockchain, and you don't really know what that address is. So you essentially have to index the whole blockchain. That's why there's no subgraph for taxation today, or there's no subgraph for token balances. So the way token balances are stored on the EVM, especially with the ERC20 format, is that the balances is within the storage of a contract, which means if there's 200,000 contracts on a chain, then there's 200,000 disparate storage elements that have your token balances in. And the only way to get token balances is to index the entire chain, which is the approach that Covalent takes. So those are some use cases, very obvious use cases where it becomes impossible in the subgraph paradigm. So fundamentally, that's like the difference between the ETL, the subgraph, and the Covalent approach. There's a lot of like other effects, like it's a unified schema and so on. But we've just taken that, initial core of an idea with the pipeline and brought it to the decentralized fashion with the cryptographic proofs.
I really appreciate the explanation, primarily because I see how the applications of this might work in the downstream aspect of things. For example, a few weeks ago, we had a presentation where I think you built a POC of a single API call that gathers all the balances from every single chain that you might have a balance on. And applications like those require this kind of infrastructure available where you are able to aggregate or have functions that run across multiple chains and then get it all at once instead of having to do it step by step for each chain. And I think that's like a very strong advantage as the world moves towards multi-chain paradigm.
So phase one was extracting these, we call them block specimens. And it's a set of patches and an open source specification on top of Get or Aragon, the standard clients for Ethereum. And what it does is it does bulk exports of block data, including all of its constituent elements like transactions and receipts, and some other pieces that are not actually available to the RPC.
That's correct.
And it does this in a synchronous fashion, the extraction. And then you can do the processing and the ingestion asynchronously downstream without actually halting the node. So fundamentally, what we're doing is the node today does a lot. It does consensus, it does block execution, it does storage. And what we're trying to do is just create a modular stack where the data of the blockchain, which is quite distinct from the execution and consensus layers, is moved out to a separate specialized system like Covalent Network. So that was what phase one was. It's been running for the past year, almost, actually more than a year. There's been 12 validators. Even with certain challenging situations with the Nomad hack, the network actually never stopped. So that's really cool to see that the network has been unstoppable and has been quite rock solid. It's a testament to our engineering team's prowess. And so That's cool. Okay, now you have these block specimens, and the block specimens are put onto IPFS,
Yes.
and then you have a manifest on a proof chain, which currently lives on Moonbeam. So you
Yes.
can go pull out all of the manifest and the IPFS content hashes of the block specimens.
Yes.
And then what?
Yeah, so this is where the refiner comes in. Because the block specimen is inherently a raw binary data object, you want to be able to read from it and derive insights from it. And there's a lot of things in there that need to be unpacked. It's a packed representation because the network has to be bandwidth efficient and processing and storage efficient. So we only put things in there that we really need, but don't bulk it up. Downstream from having a block specimen, we basically listen to events that are happening on the proof chain smart contract, which is on a public blockchain, Moonbeam. As soon as we know a block specimen has been finalized through consensus, because we do this proof of stake sort of consensus with the 12 validators in a smart contract, we don't have to have a separate blockchain node right now. But of course, in the future, we need proofing, scaling, and we'll talk about this. So now you have events that are being emitted about the finalized block specimens. You listen to them and you pull them down, and now the refiner's work starts. So one of the core things that we wanted to think about as we go through this was the ability to execute multiple block specimens. As I mentioned before, we don't have a serial bottleneck because the block specimens are independent representation. And so all we need is a content ID, and we can pull that. And we can pull multiple simultaneously, and we can initialize an extraction transformation pipeline for each one of them concurrently. And we use Elixir and Erlang runtime underneath to do this. And we have plenty of advantages like fault tolerance, high throughput, very low latency, which we can gather as a result of using the Erlang runtime. And so once we start a pipeline, the basic processes in the pipeline require stateless execution of a block specimen. By that, what I mean is we have a tool which takes the specification of the Ethereum virtual machine and is able to run on the inputs of the block specimen, the input being all its block data, all the transactions, all the pre-state, and then produce output, which is a one-to-one representation of a block that you would get from an RPC called to this blockchain node. And so you do the stateless transformation, and now you're ready to upload this again, because each data object in the Covalent network is an independent entity. We have an IPFS interactor. We further have a proofing transaction to make sure that all the validators that are doing this agree that the proof transaction matches the one that someone else produces. And in the proof transaction, we have the hash of the content of the transformed data. So they have these individual queues of work being done, but finally we need a linearized state of all the work that's been done. And this is where we make a transaction about the proof on the proof chain smart contract, which has been extended for the refiner. Now we have two deployments, one for the block specimen and one for the refiner. And here you have the block result. And this is now the usable form of the block specimen data that you can pull in, index, and start working with for queries.
There's two things that are important to note here. One is that it's a re-execution.
Yes.
Outside the memory space of a node.
Yes.
So you have basically all of the world's compute available at your fingertips. You can facilitate things like parallel execution.
Yes.
I'm not sure if parallel execution is actually that important because the blockchain state is linearized. So it's only after the fact maybe to backfill that parallel processing is important.
Yeah.
But synchronously, it's still sequential. Correct me if I'm wrong.
I can give a couple of examples where this could become an advantage. For example, right now, the stateless executor is the Ethereum virtual machine. Now, just to build on that example, suppose in the future we have a tracing engine that we can run on the EVM by basically taking intercepts from different parts of the stateless execution and storing them. And we have one version of it deployed right now. And we deploy another version in the future because we found a bug or we wanted to extend the data set that we're collecting. And now you have to run all of this again. Because of the way that the refiner is structured and engineered and designed, we can concurrently run multiple versions of the plugin simultaneously, which means we don't have to wait for one execution to finish or one plugin to do its work. We can have multiple targets. In the sort of design parlance, we have a source, a transformation, and a target. And this forms a tuple. And as long as the source remains the same, you can change the transformation and you have a new target. And you can have multiple such tuples be accessed and producing a pipeline. So you can run a lot of workloads on different transformations, different kinds of plugins through this design analogy. So in the future, when this becomes more of a thing, as the number of blocks increase and you have more number of people contributing towards different kinds of transformations, this will become a really crucial thing to scale.
Incredible. So fundamentally, it's like media transcoding, where you have multiple output formats. You have formats for low bandwidth devices, for high resolution television.
Great example.
From the same raw footage, essentially.
Yes.
Okay, incredible. Now, these transformations itself is super interesting. Basically, we are opening up a marketplace for these transformations because the demand side end use cases is numerous.
Yes.
It could be machine learning. It could be to train in a language. Maybe you want to project the data down to a small subset. You don't need all of the blockchain data. You only care about a single contract or a single like wallet address. And so you can do all of these things and just have these hyper specialized data pipelines, and this refine a framework helps with all of those things.
Exactly. The design specification allows us to think in the source, transformation, target analogy, and this extends the use cases of where you have a lot of consumers of the data and each of them want to slice and dice it in the way they like. The core element to this is understanding the block's specimen specification, but once you understand the specification, you can do n number of things with it, deploy n number of data extraction tools with it, and just use it in the way as customizable to your needs without having to rely on a data source provider to have to transform that on their site. And because it's so lightweight, you can run it on your machine.
Great stuff. Another key element here is that when you're in the memory space of a block specimen that is being re-executed to a block result, you don't need access to another RPC node.
No.
Like, it's all self-contained.
Absolutely.
If you need to do lookbacks, then perhaps you have to load an existing block result or something prior. But if it's just within the execution environment of a block, that single container is completely self-contained, and it has all the information that it needs to propagate the network after the fact. It's post-facto propagation. That's incredible.
That's true.
So you can introduce a tracing element here to trace, contracts, rights, contract, whatever you want. So it's really good for debugging. It's good for security analysis. It's good for data applications like the Covalent Unified API. Lots of things. I think it's pretty exciting. What's the timeline for all of this to going out? What is the next steps here? How can people get involved?
Basically, the big announcement is that we are releasing this framework out into the world. And we have a testnet that's going to come up. And the testnet will allow up to 50 people to run their own refiner on their machine. And requirements are extremely low. Like, you can get away with a 4 gigabyte RAM machine, like 2 core processors and like 80 gigabytes of like storage, because everything is done statelessly and everything is uploaded in the end to IPFS. You don't need access to an RPC, which is really high demand workloads right now, especially with the execution and the consensus separation. Greatly require a lot more competition to do that. But because we don't need any node access, all we need is an access to the underlying manifest, which is the data on Moonbeam, and your machine. So it'll just pull the files, it'll transform them, it'll make a proof, and it'll upload them all together. And once we have a bunch of validators coordinating to do this through having staked a bunch of CQT, we reward them for that work in CQT as well. They collect these rewards, and that allows them to like say that, hey, I've been contributing to the development of the network and propagation and securing it. And now what I can do is I can have a list of all the block results that I've produced, and anyone downstream can then pull all these block results either from his local directly, if he decides to serve it, or from IPFS. And then the applications are immense. So that's the coming few phases. We'll focus more on tying the demand side to being able to index this data and being able to extract insights from it. And when we want to do that, we're also moving towards this idea where an insight derived from an independent data extractor can be proved by a transaction that he's making. And so as you see, with the number of phases that we're growing, the number of proofs are increasing because each one of them has to state something about what their work they've done in a public, transparent layer. And we are currently building that out. So we're conceptualizing the design of how this would work for many proofs, for many validators, because n number of validators into n number of proofs is n into m number of transactions. And we have to be able to finalize them. And that requires gas. And so we have to find out ways to optimize the system at the same time, not losing the core objectives, which is transparency and security and access to the blockchain data. Yeah. We invite people to understand what the refiner is doing. We invite people to understand the specification and just let it run for a week, see how it goes. We have dashboards built in through which they can analyze how good their work is and what kind of block results they have produced. They can make blog posts about this technology and how it's going to improve the efficiency of data access in the blockchain space, especially for Ethereum, because we're focused on Ethereum. They can write tweets about this. They can make threads. There's plenty of options, and we'll list them out as we make the announcement for the applications, and we select people from those applications to run the refiner.
Incredible. Okay, really exciting.
Yeah.
So there's an incentivized testnet kickoff happening very soon, and we're soliciting applications for that. And there's a bounty for people to contribute to this incentivized testnet. The top performers from the testnet will get an opportunity to participate in the actual Covalent network, the production network.
Yes.
This was incredible, and I learned a lot. So thank you for your time.
It's been a pleasure, Ganesh, and hope to have this again soon.